How are things going? Anyone have any questions that they want to bring up before we get started? I actually wanted to ask Caitlin's group, Caitlin and Michael and Priya, I think you guys were able to track down that really tricky bug, right? Did you actually find the bug, or did the refactor mysteriously solve the problem?
Yeah, the refactor mysteriously solved the problem, which is kind of what we expected. We just like moved all of our code into the test bench module. And I think like maybe something with the clocking like worked out, but I think it's done. I think it works.
So you aren't instantiating so all of the logic lives in the test bench module. You aren't instantiating separate modules?
Right, yeah. We put it all, because before we had like the clocked integrators within the combinational blocks. And so we were just like, okay, we're not going to worry about that anymore. We're just going to put them all into one module. Yeah, so then the test bench like outputs and calls to itself essentially.
Interesting. Okay. It'll make that'll make the transition to the FPGA a little trickier because you're not going to be able to sort of drag and drop a module into Quartus, but it's good to know that the logic all works.
Yeah, that was the weird part because we literally just moved our code to another section and then it decided to work. So
I hate that. I hate that. That is so unsatisfying.
I know.
It's a clue though. I need to think about that. Maybe that does tell us something.
Yeah, I think like, I don't know. I think we all, like all of my team members expected that we were just going to refactor the code and it would mysteriously work and we'd just kind of accept it. I guess we'll have to figure out why it works for future points in the lab, but for now we're just kind of like, okay, we're done with it.
So it would be interesting to see if the original code works correctly on the FPGA because the clock assumptions are slightly different. I mean, it's a real clock. It's not a software construct of a clock, right? But yeah. But the 3D phase plot looked good. The factor plot looked good.
Awesome. Yeah, because as soon as we saw like the 2D plots, we were like, okay, I think this looks good. But yeah, that's very good to hear that the 3D plots also look correct.
There was one other group that had the same symptom. I think, how?
Yes. Yeah, any progress in the same bug on your end, or are we still working on that?
We spent some time during the weekend, but still didn't figure out. We do put all the things into one module, but still have the same issue.
So I wrote you a note in Piazza over the weekend about if the row is too high, and that you get exactly the behavior you're seeing, with the implication that you might have a 2-bit error someplace, a 2-bit shifting error someplace in either your initial conditions or your parameter set. We looked for that Friday, but did you try dropping the row to 1/4 of what you had before, which would be 7?
I tried 10, but still doesn't work. I tried 10, but it seems like it's oscillating for several periods, then goes to steady state. I tried 20, but still the same issue. So I guess 10 is too small or something.
Well, I mean, the obvious thing to do is, if you think it's a factor of 4 too big, is to make it 1/4, right? Which would be 7.
Okay.
But that's an easy thing to try. I don't know if it's going to work or not, because I couldn't see any error in the code last week. Oh well, anyways.
If you can make it to lab today, we can continue to debug this together.
Sure, I will come.
Okay, sounds good.
Thank you.
Yep. Any other questions before I get back to today? I'm going to continue with the busmaster stuff, finish the example that we started last time, and then do a slightly more involved example that involves the audio system, but that's also a busmaster. It's sort of relevant for lab 2.
Yeah, I have a question. So in the lab 1 checkoff, it says that for week 2, we need to demo signal tap or OLA connected to your solver to debug and display the 3 solution variables. Basically, it's just so that you guys can check that we know how to use the on-chip logic analyzer. Are we going to learn how to do that? Is that still expected for this lab?
That is still expected. I wasn't planning on going over that, taking lecture time to go over that. I certainly can if folks want me to. The web page associated with both Signal Tap and OLA are pretty well written, and I think if you follow that, you won't have any trouble demoing it. The idea here is just that, you know, they're very, very useful tools. So we just want you to get comfortable with it one time and just show that you know how to fire it up and plug it into your system so that you can use it on subsequent labs.
So from my viewpoint, a sufficient checkout would be if you were able to display the same plot that you displayed in Model Sim. So you display the X, Y, and Z variables as a function of time on in the debugging, and I would strongly suggest using Signal Tap rather than OLA. I wrote OLA. It was an experiment. And I occasionally like to do experiments on the class. So I gave them the choice of that last year, and they pretty much decided that they like Signal Tap better. Has anybody tried either one?
Take a look at it, and you know, you'll be looking at it in lab in all likelihood. And if it seems like it's causing folks trouble, then we'll take some lecture time to go over it. But I think you'll find that it's pretty simple to use.
I found Signal Tap to be easy but picky. That's why I wrote a really detailed web page so I could remember from year to year how to use it.
Any other questions? The other question I've gotten from a few groups is, what is the advisable way to do a reset without access to the push buttons? I would advise using a parallel I/O port, and in the audio example that I'm going to show you, I modified that example to be reset through a PIO port so that I can show a way to do this. There are a few ways that you could do it, but resetting on a parallel I/O port is probably the simplest way to emulate that button push reset that is used for a lot of the examples on the course website. Okay. Okay, just interrupt me if you have any other questions, but I'll get started on the stuff that I was going to go over. So I will remind you that what we were doing last time is we were looking at a simple example for the busmaster. Where's that page? Here. Where the busmaster is a piece of intellectual property that you can drag onto the Avalon bus, just like you were with parallel I/O ports, but that allows for you to control peripherals from within Verilog. The advantage of this is you don't have to send information from the FPGA over to the HPS and then back to the FPGA to control peripherals. So you get a speed increase that can be pretty significant. If you look on the Busmaster webpage at some of the later VGA examples, which I'll go over in lecture in probably a couple of weeks, but if you want to look ahead, those very starkly show the speed increase that you can get from using a Busmaster as opposed to going through the HPS. So that's the advantage of these things. And I will just remind you that we're looking at the data sheet for this here. So when you drag one of these onto the bus and you double click the export button on the conduit associated with that module, it exposes in your Verilog these 7 signals that we talked about last time. So the address, write data, the read and write signals, byte enable, the ACK that you get back, and then any data that you're reading from the bus. And I'll remind you too that, that this is the protocol by which all of this happens. So last time we were looking at a bus write, and I'm gonna very briefly look at that again just because it felt a little bit rushed. But when we're doing a bus write, we set the address that we are writing to. We deassert the read enable, assert the write enable bit, set byte enable to however many bytes we want to send over the bus. We set the, we shift the data that we want to send over the bus into this write data wire. And then we wait for the acknowledge. And once we receive the acknowledge, we know that the transmission has taken place. And then similarly to read data from the bus, and we'll look at this today in Verilog also, just to remind you. We set the read address, the address from which we want to read. We assert the read enable, deassert write enable, set byte enable to however many bytes we want to read, wait for the acknowledge, and then upon, when the acknowledge asserts, the data is ready to be read from the read data line. And in a cycle, it'll be gone. So you sit, your state machine will sit and wait for that bus ACK, and when it receives that bus ACK, you'll read the data and then move on. Okay. So in Verilog, well, let's look at the QSys first. So I'll remind you the system that we were considering. All that we were trying to do with this example is we want for the user to be able to send a number through a parallel IO port into the FPGA. That number will then be sent by a bus master. The bus master will do a bus write to an address where the LEDs are located, so that we can send information through a parallel IO port from the ARM. The bus master will then communicate that to the LEDs and they'll illuminate. That's the bus write aspect of this example. And then we haven't talked about it yet, but the bus read aspect of this example will be, we'll point the bus master to the address where the switches live. It will read the state of the switches and communicate that information through a separate PIO port back to the ARM and print it out. So the read and write in this case are totally decoupled. We can think about each independently. We're doing a bus write to the LEDs, and then we're doing a bus read from the address where the switches are located. So the QSys for this is not tremendously complicated. As usual, we have the system PLL on here and we have the ARM on here. The PIO ports associated with the bus write are the ones with the LED prefix because we're writing to the LEDs. So we've added our bus master here to the QSys layout, so it's on the bus here. When we add the bus master, because this is a master and not a slave, it is creating a new lane over here to which we can attach bus slaves like PIO ports. So we added this bus master, hooked up the clock, hooked up the reset lines. It created this lane to which we can attach slaves. And then we double clicked here to export all of those control signals into our Verilog. The byte enable, everything that we just considered, all of that gets exposed into the Verilog so that we can build a state machine around it. And we'll look at that in a second. So we added this to the bus, and then we added a couple of PIO ports. This first PIO port called LED display, we hooked the slave input of this port up to the Avalon master. So this is being driven by the bus master in Verilog. And you'll notice that this slave input has no connection to the ARM. So in all previous examples, before last time, we had hooked our PIO ports up to either the AXI bus or the lightweight bus so that they were being driven by the ARM. In this case, we've completely decoupled the LEDs from the ARM. They're being driven totally in Verilog by this bus master. Now, in order to tell the bus master what we want the LEDs to display, we have another PIO port here called LED command, which is hooked up to the ARM so that we can communicate a value into the Verilog. It will be sent by the bus master to the LEDs. And that connection between this PIO port and the bus master is in Verilog. So that connection is not visible here in QSYS because we do that connection in Verilog by connecting some of these exported conduit signals. So this is what we looked at last time. And then before I talk about the read stuff, let's look at the Verilog associated with these bus writes. So by double clicking this export down here on the bus master, on this external interface conduit, that exposes all of our control signals into Verilog, which show up down here in the computer system module. We tie each of these QSYS generated signals to our own wires and registers that we define above in the Verilog. Okay, so this is the handles that we'll be pulling on in order to control this bus. So these are the 7 signals that we talked about in the data sheet. Our PIO ports also get exposed here in the Verilog. So we tie our LED display port. This is the PIO port that lives, that is being driven entirely by this bus master, right? This is the one that's decoupled from the ARM. We tie these directly to the LEDs. So this is the name of the line defined way up above where all of the I/O is defined for the top level module. This is the register name associated with that hardware. So when we write to this, we are writing to the actual LEDs. So down below in the computer system module, we've tied that PIO port directly to that hardware. And then the other PIO port we've set up like we've seen before, where we've given it some name and we'll drive this one from the ARM. And then in the Verilog itself, underneath of all of the ordinary I/O declarations, we have, we declared a 32-bit wire called LED from HPS. This is the PIO port coming from the ARM that we're sending the command in through. We have a register to store the value of those LEDs. And then we have all of the controls for our bus master. And then the actual state machine for doing these bus writes is it's quite simple. So what we do is we drop into state 0 and we wait for the value being sent over the PIO port to be different from the value that we have stored for that PIO port, which is to say I only want this state machine to run when I type a new value into the PIO port, right? So when I type in a new value, the value on the wire coming from the PIO port will be different from what I have stored in the register for that PIO port, so this will run. In that case then, we'll set the state to 1, so we'll go to the next state. We will store in this register the current value that we see on the PIO wire, so that unless this changes again, we'll get stuck here until we see a new value on that wire. We set the data that we want to write to the bus to the value that we see on that PIO port. So whatever number we punched into the PIO port and sent in, that's the value that we want to write to the bus. We want to write 2 bytes. And we set the bus address that we want to write to hex 20. Where does this come from? In QSYS, these LEDs, right, live at hex 20. The LEDs which are on this Avalon bus, right, this bus master's bus, these live at address hex 20. So when we're writing a value to this bus, if we want to write it to the LEDs, we'll write it to hex 20. And then we assert the write signal. We then wait to receive a bus acknowledgement. And in the case that all we were doing was bus writes, then I would set this state back to 0 and we'd go back up here and I would deassert the bus write. In this case, I have it going to a subsequent state which does a bus read, which I'm going to talk about in a moment. But this is what we talked about last time, which gives the behavior that we saw last time, which is, oops, that's the wrong window. Which is that, oops. We can send some value over this PIO port. So we could send, say, 1, and 1 will get illuminated on the LEDs, right? Or whatever value we want. Okay. So this is as far as we got last time. What I want to look at now is the bus read, which is not tremendously different than the bus write, but we should look at it. Any questions about this stuff before I talk about the bus read stuff that's on here? See it in chat. Oh.
Hunter, can you talk a little bit generally about like how external bus masters work with several peripherals connected to it? Like right now we have the LED PIO port as a slave. What kind of situation, like, could you have multiple PIOs connected to that, and how would you efficiently write to different peripherals connected to the same external?
So Bruce can correct me if he disagrees with this, but each of those slaves would live at a different address. So if I were doing, say I wanted to be able to have the bus master do bus writes to a bunch of different slaves, by pointing it to the particular address associated with each of those slaves, I would be able to have many slaves on the same bus and communicate to each one separately. Just like we did when we were hooking up PIO ports to the ARM, right? It's the same kind of thing where we could have multiple PIO ports at different memory offsets and write to each one separately. It's exactly the same thing. We're just doing all of this in Verilog now.
Got it. Cool. Thank you.
Any other questions? Okay. So you'll notice that these LEDs are not the only slave that we have hooked up to this external master. The other one is another PIO port, which I've called the switch slave, which is hooked up to the clock and reset lines as usual. It's hooked up to the Avalon master, and then it is exported into the Verilog. This one is, I will point out, an input as opposed to the LED displays, which were an output. This is an input because we're reading the state of the switches, right? So we're not writing to the switch memory addresses and having the switches switch themselves. We're reading, the switches are inputs to this bus master. So this PIO port is an input. I'm clarifying this because I made this mistake when I was putting this together and I couldn't figure out why the hell this didn't work. And it's because I had declared the switches as an output. So this has to be an input. So this is a PIO port that is hooked up to the external master and is not connected, just like the LED display. This has no connection to the ARM. A second PIO port called switch state, this is the one that we use to communicate the state of those switches back to the ARM so that we can print it out on the command line and see what the state actually is. So this is hooked up to the lightweight AXI master. So what's going to happen here is we're going to point the bus master to the address of the switches. We're going to read the state of those switches, and we're going to put that value into this PIO port, which will communicate back to the ARM so that we can access the memory address associated with this PIO port, in which we've stored the state of the switches, and read them out. So in Verilog, we can start by looking at the QSys generated computer system. These are the two PIO ports that we were just looking at in QSYS. This is the one that is entirely driven by the bus master and is totally decoupled from the ARM. You can see that we've tied this directly to the switches. Much like this was tied directly to the LEDs, right? This was an output. When we write to here, the LEDs will turn on. This is tied directly to the switches. When we read from here, we will be reading the state of the switches. And then this other PIO port, which we're using to send information back to the ARM, this, just like this one, is set up like you've been experimenting with, where this is some wire that we've declared in our own Verilog, so that when we write to that wire, we can send information back to the ARM. So if we come back up here, we've gotten this far in the state machine, right? So this was the bus write. After we do this bus write, we go into state 2, which starts our bus read. When we get into state 2, we send the state machine into the next state, which is state 3. We assert the bus read line. We've deasserted bus write up here. We want to read 2 bytes, so we do bus byte enable is 0011. And we set the address from which we want to read to be 0. We set this to 0 because in the QSYS, we've put this IO port at address 0 on this Avalon master. Okay, so we're pointing it to this base address, this offset from base address. And then we sit here until we receive a bus acknowledgement. When that bus ACK goes high, the data is available to be read on the bus read data line, which is declared up here, and which you will recall we have tied to the read data QSYS generated line down here. Okay, so when that bus ACK goes high for a bus read, that means that for this cycle, we can store the value of, on this bus read data line in some register. And in this case, I've stored it in something that I've called switch register, which just stores the value of the switches. It's just a 32-bit register. And then in order to actually communicate that back to the ARM, I have this switch to HPS wire being always assigned the value of switch register, just like we've seen before for PIO ports, right? Where this switch to HPS line is the one that we've tied to this other PIO port that communicates back over the lightweight bus to the ARM. So this example takes a value from the user, sends it over the PIO port, puts that value into, so this is the value that we get over the PIO port. It puts that value into the bus write data line and writes it to the address where the LEDs live. So the LEDs show the value that we've put in. It then points the bus master to the address where the switches live and asks to read from there. So it gets the value of the switches. Stores that value in a register, and then sends the value that is being stored in that register over a PIO port back to the user. So as I mentioned last time, this example is for understanding the mechanics of how these bus masters work, right? This is not a super practical example. Right? It's not clear why you would put together all of this infrastructure just to like write LEDs. You'd probably do something simpler than that. But it is a simple canned example for understanding how these bus masters fit together. So then you can see that when we're doing when we write some value here, in addition to illuminating the LEDs with the bus write, it's reading back the state of the switches, which for this particular board happens to be 03 CE. So If you convert that to binary, that's the state of the switches. And I mentioned last time that if you want to run these sorts of tests on your own boards, the way that you can check the state of the switches without being able to walk into the lab and look at the state of the switches is, before doing this, put together a simple Verilog that just ties the switches to the LEDs and see which LEDs light up. So that you can say, okay, switches number 1, 7, and 3 are flipped, or whatever it may be. So then you know what the right answer is, and you can confirm that you're getting the right answer back. Does this make some sense? So this is a tricky thing to treat in lecture, right? Because the only way to really present it is to sort of show you the whole thing, and then try to pick it apart. So that's what I'm attempting to do here. And I'm going to keep doing that a few more times with a few more examples. But like I said, it's like everything in this class where it fits together with everything. So it only makes sense when considered with everything else, which makes it a little bit hard to see for the first or even second time. But as you start to play with it, it becomes clearer. Okay. So should we look at a more practical example, perhaps? We can look at a bus master for the audio interface. So let me see here. I'm going to close this and open up a separate example for the audio interface. And while this opens, I'll show you. So while this is opening, I will show you where I got this example. On the Busmaster peripheral page, I downloaded the audio output Busmaster example, and then I made a few modifications that I'll point out. But if you're looking for a place to start, this is where I got the foundation for this example, and then just made a few changes that I'll point out. The changes that I made are I have it resetting over a PIO line instead of a button push. And what this particular example actually does is direct digital synthesis of a sine wave. And in the example, you set the frequency of that sine wave with the switches. I've modified it so that that frequency is instead controlled over a PIO port, so that I can put a value in and the frequency changes instead of flipping switches. So these are the types of modifications that you'll likely be making to a lot of these examples, since you can't be throwing switches yourselves. So perhaps it's worth taking a look at it. And if I can get this, I don't know if we'll have time today, but I have this tied to so this does direct digital synthesis. So it'll produce like a tune of at a certain frequency, which ordinarily you plug into a speaker and you just hear that frequency come out. I have this instead plugged with an aux jack into the microphone input of the host PC in lab. So I was testing this yesterday. So I should be able to join this Zoom call from the lab PC and run this example, and the FPGA will sing to us through Zoom, which is a capability that will be relevant for Lab 2 if you want for your drum to drum at you through a Zoom call. That's how you'll do this. We'll see if we get that far today. If not, then I'll do it next time. The thing that I'm working on that I haven't gotten figured out yet is I want to get full audio loopback working through Zoom. So I want to be able to talk to the FPGA through a Zoom call and have that go through the headphone jack of the host PC into the FPGA fabric, and then come out through the DAC into an aux jack into the microphone input and talk back into the Zoom call so that I could say hello and the FPGA would say back hello. What I'm working on is how to do that without creating a feedback nightmare. And I think the answer is going to be maybe having 2 Zoom calls open with strategic muting, but I haven't gotten that far yet. But it would be pretty cool for final projects, I think, because then you could talk at the FPGA and do signal processing on that talking, maybe doing closed captioning. That would be pretty cool. Maybe doing like Post Malone style auto tuning. I don't know. There's a bunch of opportunities to become available if you can do that. So I'm trying to get that figured out. In any case, let's look at the Verilog for this audio example. Actually, let's start by looking at the QSys. Actually, even better, let's start by looking at the data sheet. Video core, audio core. So this is where the data sheet lives for the audio core. And I'll just point out a few things here. So it is the nature of audio that consistency and sample rate is very, very important. So this system's audio sample rate is 48 kilohertz, which means at 48 kilohertz, there better be a sample ready for, if you're outputting audio, there better be a sample ready here every 48 kilohertz to send out to the speaker, right? Otherwise, you're going to detect it with your ear. Your ears, it turns out, are super sensitive to things like this. So at every 48 kilohertz, there better be something ready here to send out. The way that they ensure that for this particular system is there's a FIFO for both the left audio channel and the right audio channel. So the Avalon switch fabric, the Busmaster, it tends to be a little bit bursty. So in order to guarantee a 48 kilohertz sample rate, we fill these FIFOs, and it's okay if we fill them in kind of a bursty manner, and then we sample them, the system samples them at exactly 48 kilohertz. Okay, so the registers associated with this system is, there's a control register for setting things up. There's a FIFO space register, which will tell you how much space is available in both the left channel and right channel read and write FIFOs. So if we want to put a sample into the queue essentially to be output through the DAC, we'll start by checking how much space is available in the output FIFOs on both the left and right channels. If there's no space available, then we have to wait. And we'll just wait until there's space available, and then we'll fill in the next sample. And the same is true if we're sampling from something like a microphone. We check the availability, how full the FIFO is before we try to put anything in there first. So there's sort of an extra step in our state machine that will become clear in the Verilog, where we have to check how much space is available in these FIFOs. And then there's left data and read data registers. If you write to these registers, then you're sending data out through the DAC. If you read from these registers, then you are sampling input from the ADC. And if you scroll down, you can see some details of these things. So these are just some details about what each bit in each of these registers mean. So the FIFO space register, for example, you can see that the first 8 bits are the left channel right FIFO space. That's where the left channel right FIFO space availability information lives. The next 8 is for the right channel, and then the right channel read availability and the left channel read availability and the right channel read availability. I don't know why this horizontal resolution was used, but whatever. And then some information about the control register for setting things up.
Okay.
Yeah.
The offset in bytes here is from the address specified on QSys?
Yeah, so if we look at the QSys, where we added the audio system here, it would be, in this case, offsets from hex 3040. Okay. So we can take a look at this. Again, system PLL and ARM as usual. The AV config module, which sets up your audio system. The audio system itself, which is, what do I want to point out about this? I will point out that the audio slave input is hooked up to this bus master. So we'll be driving it from this bus master. A bus master here, which is the same module that we were looking at in the previous example. This one has been given a different name. So just don't be confused by that. This is just, recall whatever name we want to give this, we can give it, but this is a bus master. And then a PIO line that I added to this example to put the system into a reset state. So if I set this PIO to a certain value, it's the equivalent of me holding down the reset button. And then when I set it to any other value, it's the equivalent of me letting go. Okay, so let's look at the Verilog. And we'll start by looking at the QSys generated stuff. And this is the reset PIO line that looks familiar. This is the same sort of PIO line that we've seen many, many times. We tie the AV config generated lines to the I2C clock and data lines. Turns out this configuration takes place through an I2C interface. So we tie these to the I2C lines for the FPGA. And then the audio subsystem, which is tied almost entirely to hardware that is defined at the top of the top level module. So much like in the previous example, we were tying things like PIO ports direct to LED hardware. In this case, we're tying, let's see, where does it actually live? It's somewhere up here. Here. So here's all of the actual audio hardware that goes out to the audio system. In this case, we're tying the exported audio interface that gets exported from QSys into Verilog. We're tying that to the actual audio hardware, as shown here. And most of this stuff has names that suggest precisely what it's tied to.
There is a significant chunk of hardware which is off the FPGA, which is the audio codec. So there is a separate chip which hooks to the microphone port and the headphone port and is the target for the I2C bus, which, and it itself is a monster DSP machine controlled by the FPGA. One reason for needing the reset line here is that if the two state machines, your state machine and the state machine on the audio codec, get out of phase, you get an interesting selection of noise. Interesting meaning here, ear splitting. So that's why you need a reset line.
So we can take a look at this. We'll just take a look at the state machine. You can see that in the case that reset PIO line is precisely equal to 0, then we're in a reset state. The state gets set to 0, bus read and write gets set to 0. We're resetting this timer, which is just being used to see if things are running. And in order to see visually that we are in a reset state, I created this register called reset status, which is a 10-bit wide register. And I am always assigning the value of the LEDs to the value that's contained within this reset status register. So in the reset state, I'm setting that to a whole bunch of ones, which means when I'm in reset, all the LEDs light up. And then when I leave reset, all the LEDs turn off. So just a little bit of visual information about if I'm in the reset state or not, which is useful for debugging. But when I drop out of the reset state and I drop into state 0, then I set the, I want to do a bus read to see if there is space available in the FIFO. So I set the bus address to the audio FIFO address, which you can see up here is 4 is, what is that? 4 above the audio base address. Why is it 4 above the audio base address? That comes from the data sheet. Right? It is offset by 4 bytes from the audio base address. So that is where the audio FIFO information lives. We want to read from that address, so we set the read to 1. We want to read 4 bytes, so we set bus byte enable to 1111, and then we move to the next state. Before we drop into this state, we wait to receive an acknowledgement from the bus. Set the state to 2. Determine the FIFO space by shifting the value that we read at that audio FIFO address register, shifted by 24. Why? Again, that comes from the data sheet. Shifting by 24 means we are reading the left channel audio write availability. Okay, so we see how much space is in the FIFO, and then we deassert the bus read signal. In the case that there is space in the FIFO, in this example, we're actually checking to see if there's 2 slots available in the FIFO. In principle, there could only be 1 available, and you could do this as far as I understand. In the case that there is space in the FIFO, then we set the state to 3. We do some DDS phase accumulation. And here too, this is the other slight change that I made. In the example on the website, this is the switches. In this case, I'm just using the bottom 10 bits of the PIO line. So I do a little bit of DDS phase accumulation, and then I want to write, which I tie to a sign table, just down at the bottom. I can show you in a moment, but I imagine you've all seen this DDS stuff before. So I want to write a DDS output to the DAC. So I set the data to be the output from my direct digital synthesis sign table. I set the address equal to audio left address, which is defined up here. Again, this is at an offset from the base address that comes from the data sheet. I want to write 4 bytes, and then I set bus write to 1. And by the way, if there was not space in the FIFO, so this was all in the case that there is space in the FIFO. If there was not space in the FIFO, I go back to state 0 and I try again until there's space available. And I'm out of time, so I won't continue this example now. But next time I will start with this. We'll go through this audio example, and I'll try the Zoom thing here to see if that works. Any questions or concerns?
Is code going to be on Piazza, or you want me to put it on the web page?
Oh, this code here? I haven't thought about that. I guess I could send it to you if you wouldn't mind sticking it on the web page. Maybe then everything's in the same place. Okay. Anything else?
I had a question about signal taps. You said you want to see the same waveforms that we've seen in Model Sim. It looks like signal tap only shows like bit by bit. Like it'll show like like all 32 bits for whatever signal you're sending X, Y, or Z. So it's only going to show like one bit at a time. Do you want us to like export that data and graph it in MATLAB, or? You're muted, Bruce.
I thought there was an analog selection in Signal Tap, but maybe not.
I don't see anything, but I could be wrong. This is the first time I've used it, so I don't really know super well.
Let me look here. Post the question on Piazza, and I'll try and get an answer.